All right, what's up, guys? Welcome to the channel. Today we're going to be doing a code walkthrough through the Tokio source code. If you're not familiar with Tokio already, it's the most popular asynchronous runtime in Rust. Lots of crates and projects are built on top of Tokio, and I would consider it one of the most fundamental parts of the Rust ecosystem. And a little disclaimer about myself, I'm not a maintainer or even an active contributor to the project. I'm just someone who uses it a lot and want to know how it works. So today I'm going to be digging into the source code, focusing today on how the runtime is initialized and what happens there. And yeah, I just want to basically understand how it works. So let's get into it. So what I want to point out first is this blog post by the author of Tokio, Carl, where they go into some of the optimizations that they made to Tokio and how. They give a really good high and low level overview of how Tokio itself works, and that's a really good starting point before we dig into the source code itself. So please, I would recommend just give this a quick read over and then hop back into this video. Okay, where do we start? Um, so typically, the thing that you do when you want to interact with Tokio is you use this Tokio main macro, which is responsible for building and instantiating the runtime itself. So let's try to figure out how this works, right? So we go here, let's go to the API docs, go to macros, main, and you scroll down a little bit and you can see here that this is the equivalent code where we're calling a builder, creating a new multi-thread runtime, enabling all the features, call build to create it or initialize it, and then we're gonna block our main task onto that runtime, right? Okay, so we can actually confirm this using a cargo plugin called Cargo Expand. And what this does is it will basically expand the macro into what is actually generated. So how do we do that, right? So we're in the Tokio project itself. It has some examples in the examples directory. Okay, let's get echo. It's a simple one. And we see here, yep, it's using the Tokio main macro. And the main function, it's basically just a loop over a socket where it will echo whatever is read on the socket back to the socket, right? Okay, so how do we cargo expand this? So what we can do is cargo expand the main function of the example echo. Okay, and then it spits out basically the main function that we had, right? Give that to a task, define that as a task, so a body. And yep, it generates the same exact thing that we saw in the docs. New multi-thread builder, enable all the features, build, block on, main task, right? Cool. So then next question, what actually happens when we call build? How does building a runtime actually work? Okay. Let's go back to the docs and we're gonna look for in the runtime builder. There we go. And there's a source link here, and we can find that the definition of this function lives in Tokio /runtime /builder. So let's go back to our code here and runtime builder, right? Look for the build function here. All right, so this is our starting point. Okay, so what do we have here? Okay, we can see that there's two different kinds of runtimes. There's something called a current thread and something called a multi-thread. And remember, the main macro creates the multi-thread runtime first, right? By default. And yeah, we're gonna stick with the multi-thread here because that's kind of what we're most interested in. Eventually, what we want to do is want to look how like the work stealing algorithm works, and that's really only valid for the multi-thread runtime. So let's just stick with it here, right? Let's hop into here. Okay, let's see what we have. Okay, so the first thing we have here is core threads, which is a usize, where it can either be passed into the builder itself, or if it's not passed in, it called this function num CPUs. And so what num CPUs is it basically calls into the system and will return back the number of cores that the system has, which this runtime is running on, right? So if you have a 4-core CPU, 8-core CPU, this is what it will return. And so we can just assume here that core threads is going to be the number of cores on the system to make things easy, right? Next up, something called a driver, and we pop in here. We can see that there's something that deals with I/O. We have a clock here, the timers, and so what I think is going on here is this is the thing that kind of drives the external inputs into the system. So yeah, the I/O they get from the operating system or like the timers and such. And so yeah, we're gonna keep continuing for now. Next up, the blocking pool. Okay, so what I know about Tokio is that, or all asynchronous runtimes in Rust in general, is that you should never really block the runtime. So you should never have a task that doesn't let the runtime pull for very long, right? So let's say you're blocking on a lock or blocking on like just have a spin loop. Like this is what is gonna just hold up your runtime, and it's not gonna make any progress moving forward. So anytime you have like a long running task where it's gonna block for a long time, you actually want to spawn it to a separate, call a separate function for it, like a spawn blocking, and that's gonna spawn into this separate blocking pool so that it doesn't block your original runtime. Okay, the next step then we have the random number generating seeds. All right, so our seeds that feeds the random number generator. And the real meat of it is right here. So multi-thread new. So we hop into here. You can see that there's something called a parker. Sounds like it's have to deal with parking on parking threads or tasks. And then worker create. So what happens, or how does a worker get created? Hop in here. Okay, let's see. We have a cores vec, a cores, which is a vec with capacity size. So remember, size is the number of cores here, and remotes of the same size, and then metrics. Then for each core, it's calling local or queue local. So what this looks like here is this is where the run queue is actually being created. So let's hop back into the blog post real quick. And if you go into picking a better queue algorithm, this actually will describe how the run queue is implemented, right? So you can see here, like this is the actual code for it. And what we have here is we can see that buffer is a vec with local queue capacity, which is a static value of 256. What's interesting is like you would kind of expect this to be a configuration that you can pass into the builder. But I mean, I guess like you kind of don't really want this too big anyways. Because if you're hitting the run queue capacity, then that means like your tasks are blocking, which is not good, right? Like what I was mentioning earlier, like you kind of want your task to finish as quick as possible. So your run queue should never really get too big. So I guess that's what they're thinking of when setting this to a static value. Like we would have to dig into the Git history to kind of figure this out, why this here. But for now, it kind of makes sense, right? So this is just setting the capacity of the vec. And then what we have here is a loop, which then will kind of initialize all the memory or pre-allocate the run queue. And the interesting part here is it's using something called an unsafe cell with a maybe uninit. So what I think is going on here is that because we're pre-allocating the memory, we need a type that will let you represent that there's actually no task currently in this memory, right? Because we're just pre-allocating it, no tasks have been pushed onto it yet. It's basically none, right? So if you think about your typical option, where you have option type T, so let's say your task is this, bits, right? So initially it's set to none. Okay, but the thing here is that if you look at option, there's two states of the option, right? There's none and then there's some. So none means there's no value, some there's some value of type t. So the reason why that I think they're using maybe uninit here is because, for example, when you store an option of some type, right? So let's say the type is a U32, and we hop into here, you can see that the size is 8. But even though a U32 is only 4 bytes, right? What is the extra 4 bytes for? Is to actually represent that you need the extra 4 bytes to represent the state of none. There are some types that let you get away with not having to do this. For example, if you have like a let's say let has 2, something called a non-zero. So if you have a option non-zero of the same type, let me just import this. You can see that the size is 4, so exactly the size of a U32. Well, why is this? Well, a non-zero gives the compiler a guarantee that the type inside the U32 inside the non-zero will never be 0. So actually, the compiler can use 0, which is a valid value of the U32, to represent the none value of the option. So this is called the non-null optimization. And so this lets basically you define an option of type non-zero to be the same size as the U32, right? So it's basically a way to save memory. And I think that's what they're doing here, is that the maybe uninit, where the uninit is the state that represents the none. So the benefit here is that you don't waste any extra memory for using an option. But the only downside here is, yeah, you have to use unsafe. But because Tokio is such a well-used or well-popular crate, like this is worth it, right? To get these types of optimizations. Cool. Yeah, moving on. So yeah, then you have this type that represents, you have your head and tail pointers here. And then again, buffer. Another cool thing, another memories trick here, they're using buffer into box slice, which turns a vec into a box of t. So then, right, so buffer here is type vec, right? Whereas if you call into box slice, this turns into a box into the slice. So again, you can see here buffer. This has size 24 bytes. Oops. Let me get this correctly. Yeah. The vec is 24 bytes, whereas a box slice is only 16 bytes. Right. This is just because the vec basically stores the capacity on the stack, but the box slice just stores the pointer plus the length. So yeah, there we go there. And then the last thing is that there's actually the reference of the inner is cloned into two different types. There's the local type and the steal type. So going back to the blog post, you'll find that Carl goes into some things talking about work stealing. And what I believe is going on here is like the local type that belongs to like the worker that owns the core. And then you'll basically pass around these steal types, which are for the cores the other cores, so that they can steal this core, right? This work of this core. And you can see here, like they're kind of the type definition is basically the same. They just have the inner, but the functions are different, or the methods that you can execute on these types are different. So it's just kind of a way to use the type system to basically disallow certain operations that you can do. So if you're the core that has a local reference, you can do certain things. If you're a core that only has a steal reference, you can only steal from it, right? So that's kind of what's going on there. And yeah, so let's hop back. So that's your run queue initialization. And moving on, you have the park on park, some metrics, stats. Okay, that's all well and good. And then here is where it's creating like basically the per core data. So you can pop into here, yeah, core data. So then we have tick, last in, first out slot. Yeah. So back to the blog post, yeah, right here. Carl describes an optimization that they have to make for kind of message passing use cases. And so what this does is just has a slot right next to the run queue where it gets checked first, and that's basically just what this is, represented as an option. That's your run queue right here, and then a couple flags that represent some state, and yeah, your fast number generator. That's where the seeds that we saw earlier are gonna be going into. Okay, so that's the data that lives per core. Push that into cores, and then yeah, for the remote spec, we just push the steal type. Remember, this is the steal that's returned from the run queue itself. Here, that goes into the remote spec, and that's done per core. Okay, then we have idle. So I believe this type, this just holds a state of when the worker is idle. It has to look at this to kind of know which workers are idle. Yeah, right here it's just there's like some state that it checks that doesn't need to have a lock. Inject. So this, I believe, this is the global queue. So if you go back, there's some description of the global queue here. Yeah. So what will happen is that there's many queues, and then there's a queue per worker, but then there's a single global queue that gets checked from time to time, and that's what's defined here. It's called inject. And then last but not least, we have the handle to the runtime itself. So this is a single handle, and then we pass in some hooks. So in the builder, they allow you to define to call some callbacks like when tasks are spawned or when they're terminated. So that's where these are set, or these are passed rather. And then something called shared. Okay, so this is a single. This is kind of like a singleton that's shared across all workers. So this is how the workers communicate to each other through this type. And yeah, that's it for the handle. And then we have the launch. And so the launch, what it is it's just, if we just look at the cores back, we map it into a launch. So this is just the workers, right? Then basically all the workers are put into here, and then it's returned along with the runtime handle itself. Okay, so that's it for worker create. Let's hop back. Nope. Right. Okay, so then that finishes multi-thread new here. So then we have the scheduler, which is multi-thread, the handle to the runtime itself, and launch, which contains the vector of all the workers. So then we wrap the handle into another type here. And okay, this is where it's actually spawned. So these are actually where the threads spawn. So let's go into here. So handle enter. Okay, so you can see right away it's using the guard pattern. Guard pattern is used when we want to kind of run some destruction when something's dropped. So if you look into here, there should be some drop implementation. Maybe not on this, but also any of the fields. So this is also another guard. Yeah, okay, so we have drop here. Right, so you can ignore this for now, but yeah, so this is where the runtime is actually freed, looks like. So through this guard handle. And yeah, then we have context set, try set current, returns a guard, try set current. Okay, so what? Okay, so what I see here. So context is a thread local. We'll go into more detail here about the thread local itself. Okay, but all what this is doing is it's setting the handle that's just been created to the thread local. Okay. So what is this? This is basically a struct that is set per thread, right? Each thread has its own copy. The alternative way to do this is like, let's say you just have a global singleton like runtime handle, right? That's accessed by all the threads. But the downside of that is it needs to be synchronized, like, or otherwise you're gonna have data races. So you need like to wrap a mutex around it, or yeah, something like that. Or and what does that do? Of course, you're gonna have performance benefits. Like you're gonna have contention. Your threads are gonna have to wait on other threads, etc. So in terms of like removing the need for synchronization, Tokio goes through a thread local. And so each thread has its own copy, which means it doesn't need to synchronize with any threads. Therefore, you get some performance benefits out of that. Yeah, and then for shared state that needs to be edited, like yeah, then of course you need to go through like a lock or something, right? But for now, you don't need to do anything here, right? So enter is where the actual thread local gets set. And then you have your guard, and then we call launch here. So what all launch is doing is for every worker, spawn blocking. And I think what we'll see is we go through spawn blocking. Yeah, so this is really important here, right? So you can see here spawn blocking doesn't actually take the runtime as a parameter. What it does is it will call handle current, which then all it does is it will look at the current thread local. So this is how Tokio is able to get a reference to the runtime without you having to actually pass it in as a parameter. So really good, like yeah, user experience here, or where you don't have to you don't have to carry the runtime handle around everywhere you go. You just put in thread local, and then you'll get a reference to it. This is also why you'll see, like, if you ever try to spawn a future without actually creating the runtime itself, like your program will panic because there's no thread local set. So this is how that's detected. Yeah, just going deeper into this. Yeah, inner handle. This is your blocker, spawn blocking. And if this is some size optimizations where you either box it or not. This is cool. I didn't know this. I didn't know about this. So this looks like if your task is greater than this, so 16K, it would actually, well, if it's less than that, it'll actually go on the stack. Otherwise, it goes on the, yeah, it goes on the stack here. Otherwise, it goes on the heap. That's cool. Here's the box. Nonetheless, let's go deeper into it. Your task ID here. Self spawn task. I believe we go down more into this. Spawn thread. There you go. Help spawn thread. And yeah, so this is actually where the OS thread itself is spawned. So if you remember way back in the beginning of the video, we have one core, one worker per core by default, and then that maps to one thread. So then we just have one thread per core basically by default. And yeah, so this is actually the thread spawn here. And so this is how you get your multi-thread runtime, right? Because then now you have a thread per core. And yeah, and at this point, your runtime is ready to go. And then what's next is if you go back here, yeah, after you call that, then you call Tokio spawn on that, which we'll cover in greater detail in another video. Okay, but yeah, I think that's all I had. So if you learned something, if that was helpful, if this was helpful for you, yeah, please like and subscribe. This is my first video, so I'd love to get some feedback and see what y'all think.